Okay, we are learning about force. The definition of force is a push or pull. Y'all know what that means. Pushing something and pulling something. The thing is like, y'all have never looked at things moving and said, oh, that's the push came from here, or that was a pull. That's what we're going to do a lot of. So you just have to kind of analyze the thing's motion and figure out, was that caused by a push or a pull? Okay? Y'all can talk to me. It's okay. Number 1 rule. Forces always occur in pairs. So what would pairs mean? 2. Yeah. There's a new SI unit. Yay. It's called Newton. Forces measured in newtons. To abbreviate, it's a capital N. Okay? I'm always going to use a capital N. I don't care if you write it out, doesn't matter. But if you're reading my diagrams, it's going to have an N. Now, force has a magnitude and a direction, so what is it? Vector quantity. The one thing you haven't done yet is actually draw your own vectors out. Okay, you will have to do that. It's not hard. I just want to make sure that you understand what you need to. Okay? So let's say we're going to draw a vector for 100 newtons. Whatever direction they tell you, that's the way you would go. Okay? So let's say it's east. Magnitude is how much, and then the direction is the direction it goes in. What would the vector for 50 newtons look like? Half. Yeah. So that's all you're doing. You're making sure when you draw it, it's in the direction that they tell you, and it is the correct size. Sometimes mine aren't that great, but you get the point of how to do it, or how to read them. They should look like their size and the direction that they're going in. Okay? Now, a few examples of forces. Do y'all know any? Gravity. Friction. Sorry. Gravity, friction, and magnetism. Okay, so I want to go to the weird way of thinking for a second, okay? And we want to talk about like the book sitting on the table. What causes the book to sit on the table?
Gravity.
Gravity. Okay. Is it only gravity? Magnetism is magnets. Okay, first let's talk about this. If it's only gravity, gravity's pulling the book down, right? Then why doesn't the book go through the table? If the table's stronger than the book, then why isn't the book flying up? Well, Well, what was my number one rule? So there are two forces there. Okay? But I want you to understand, if the second force isn't there, the physics is we would go through it. So right now, your butt is sitting in the chair, but if the other force isn't there, gravity's going to pull you through the chair. Does that make sense? That's weird to think, but does that make sense? Okay, so gravity's pulling you down, but the chair's pushing you up. Gravity's pulling the book down, but the table is pushing up. Okay? And then her and I are standing, so gravity is pulling us down, and the floor is pushing us up. Okay? All of those situations, that force is called the normal force. Normal force. That is the force exerted perpendicular to the surface of an object. Now, by definition, that's kind of tricky. You will, because it'll stand out. Watch. You see these lines right here? These are called parallel lines. Okay? Because they run. Now, this right here, that's called perpendicular lines because they form a 90. That's perpendicular lines too. The perpendicular form a 90. Okay, but here's the thing. The perpendicular is basically coming out of the surface, which is weird, I know. Like, here's the ground, and here's an object. Gravity's going down. Those are supposed to be equal. Gravity's pulling it down, but the ground is pushing up perpendicular to it. That doesn't make sense to you? I was standing. Gravity's pulling me down. The ground, the normal force comes out perpendicular to the surface. That's the surface of the ground. It comes out of the ground. Because gravity's trying to pull me through the ground. The normal force is the force that, like, keeps things from passing through each other. Does that make sense? I can overcome the normal force. I could have it greater. Break the ground. Break the table. Would the book fall then? So does that make sense? Look, watch. I'm going to push on the wall. Right? It ain't moving. Am I falling through it? No. My force is this way. The normal force is the force that's perpendicular to the surface. So I push this way, and it pushes this way, perpendicular to it. Does that make sense? That makes sense. Okay, so let's draw like a wall, and then the normal force is there. Well, okay, I'm that way. But look, you see it? You see the right angle? No, it's right there. This is the normal. See what I mean? Here, okay, look, let's try this. Here's your chair. Where's the normal force? Out of the seat. Because what's gravity trying to do? Pull you through the seat. Does that make sense? Well, look if we had a slanted surface with a box. It's perpendicular to the surface, so the normal force is that. It comes out of the surface. It comes out of the surface, and look, there's a right angle right there. Does that make sense?
Yes, ma'am. What if there wasn't any gravity, and if I drop a pencil, then it's the earth trying to meet up with the pencil, and the pencil's trying to meet up with the earth? Like, the earth is moving towards the pencil.
It's not gonna. Gravity is like the force that attracts everything to each other. If that's not there, they're not attracted. So then it, yeah. Makes sense? Okay. Whew. Let's talk about net force. Net force is the combination of all the forces acting on an object. Let's draw your table with the book. Okay? Gravity's pulling the book down. True? And the table is pushing the book up. We're going to say gravity's pulling with 5 newtons and the table's pushing with 5 newtons. They are tied. Very good. So what is the net force on it?
0 newtons.
0 newtons. Oh, yeah. You do have to put the newtons. It'll tell you the numbers.
And if it was just 5 newtons going up and 0 newtons going down, then it would be
5 newtons up? Yeah, but somebody would have to be like underneath the book, pushing it up. I don't want people to, I mean, that was a great question. I just don't want people to think like, what, that happens? Yeah, no. And somebody today said something about gravity pushing you down. Think about that. Gravity pushing me down, we'd be like smashed. Nuh-uh. It's not what happens. No, gravity pulls. It pulls from our, it's called like the center of mass. It pulls from your center. That's why if you jump, yeah. Okay? Now, let's talk about this book. So, let's say I got my book over here, okay? And I'm pushing on my book right now with, we'll keep it at 5 newtons. Okay, so I'm going this way, and I'm pushing with 5 newtons. Right here. But my book doesn't move. There must be something what? Friction. So that means if I push that book and it doesn't go anywhere, something is over here pushing me back. Does that make sense? And since it doesn't go anywhere, they're equal. How do I make the book move? Okay. I need to, as soon as I have more than friction, it moves. Okay. So we're just going to, for right now, we'll go ahead and put 6. But if as soon as it's like 5 point whatever, it's, I don't know, babe. Don't know. I got to go through some new, it's all new material. Like, it's not new material, but they're changing the test. So I need to go, I'm going to have to go spend time researching their kind of questions and see if they change it. Okay? It's okay. I'm going to prepare you for it. At least you're going to know what you need. What would be the net force in this situation right here? It's a vector. Magnitude, and it can be east or it can be right. I know we've been doing east. No. I know we've been doing east, but most of the time on these, they do just put up, down, left, right. But for now, I mean, if you do east, I won't mark it wrong. Okay? Okay. Now, what about this one? 5 newtons. 5 newtons. 12 newtons, and I probably drew that too big. 6 newtons. What is the net force on the object? Magnitude and direction. Who doesn't understand? Okay, come on, Valerie. All right. You stand right here. Okay. Push. You have 5 and I have 5. Okay, look. Okay, now you stand over there. And I'm going to be here. Okay, push. Hard.
So how do you have
She has, you have 12, but I have 6. Okay, push there. We both have 6. Now push hard. You have 12. You're pushing harder than me. Which way did it go? You won. Does that make sense? You pushed harder, so you were the 12, and the thing went this way. You still felt my force, didn't you? So I still had 6 newtons, but you had 6 more than me. So you were the one who got to move the cart. You get it? You do subtract them, but I'm showing her how does that, what actually happens. Does that make sense?
Is the direction going to always be the bigger number is pointing? Like if it's pointing right, would it always be?
It's going to go in the direction of the most force. You want to know this. What happens if all of these are the same, but this is 6? If this is 12, this is 12, this is 12, this is 12, and this is 6? And these are 6 and 5? He's going to, 12, 12, 5, 5. It's going to move like at an angle. Like it's not going to go down. because it's not going to go straight down. Because this 12 and this 12 are going to work together. They're going to come together and move it like that. Well, it's harder than that, but I get your thinking. It's hard. It's a little more complicated than that because you have to take in the angles, and it's actually sine, cosine, tangent, and all that stuff. It's hard. Yes?
So you would call it southeast? Going to southeast or right and down?
Southeast, yeah. This is, okay, they ask those kind of questions, but they don't do it with the numbers. So, like, they put people around it and say, or they'll say, here's your object and I want to move it this way. Where do the people need to go? See what I'm saying? So, you would just need, that's why we do these other experiments. You'll get it. You don't have to mathematically know angles. You only have to know up, down, left, right for mathematically, okay? Okay, now, let's look at this person pulling a rope with 100 newtons. And this person right here pulling a rope with 100 newtons. What's the net force? 0 newtons. Okay, everybody cool with that? That would be where they, at the beginning of the tug of war, when they're both at, deadlock, like it's just stuck. Okay? But eventually, one person is going to outlast the other. Okay? And he's going to have 200 newtons. And he's going to have 150. And what would be the net force? Yeah, you keep forgetting that, and it's worth 3 points. They are worth 3 points. Okay?
The direction by itself?
No, babe. 1, 2, 3. Caleb? He has more. You good? Yes, we subtracted the 2 because they're in opposite directions. Okay? Now, watch this. You can stay there. I want you to put your hands right here, and I want you are going to pull that way. Okay? Ready? Go. You see how fast that went? Let's say we're moving a cabinet or something. This person pulls with 125 newtons, and then this person over here is going to push. It could just be 100. No. You saw how fast that cart just moves when her and I did it? That's because we worked together. So you add this. This is 225 newtons to the right. No, there's friction. We overcame it. I'm going to explain that in a second. What? Everybody's good? Okay. Yes. Whenever the arrows are the same direction, you add them. When the arrows are in opposite directions, you subtract them. And this is the one that's the hardest because you look at it and you're like, huh, how are those in opposite directions? But it's because he's going this way and he's going that way. Yeah, it's weird. Yeah. Okay, now I'm going to take everything we learned in motion and I'm going to put it into here. It's not that hard. Watch. So I've got this guy, and this is a skateboard. Don't laugh at my pictures. Okay? This dude right here, he wants to ride a skateboard. He looks like a midget next to it, and that's great. So I drew a stick person, so obviously I can't put my vectors on top of him. You can't see it. So I'm going to put them on the side, but please understand that's not where they really are. Okay? They'd be like, yeah, on him. Yeah, where he is. So how is he standing there? Gravity is pulling down, and the ground is pushing up. And they should be equal. Equal but opposite. Are we good with that? Okay. So, what is his motion? Standing. And what did we call that last week? At rest. It's not hard. It's not hard. But we're taking the motion and we're applying it to here. This is called balanced forces, and I'll give you the definition in a minute. But they're equal and opposite. Okay? Everybody cool with that? Now, our dude really wants to skate, okay? So, he is going to push off the ground. Okay, so his foot's right there, and he's pushing on the ground, and he's pushing with 100 newtons of force. Everybody good with that? But over here, there's like something stopping him. And it has 100 newtons of force. Okay? What is his motion? His motion at rest. This is called balanced forces. And mathematically, y'all already said the answer. Yeah, the math. Yes, y'all already said the math. The net force is 0 newtons. Nothing. He's not moving. Makes sense? Everybody cool? Now, he is determined to ride that board. Whatever. So he pushes harder with 120 newtons of force. Okay? And we're still going to have that friction over here. Whatever you want it to be, rock or just... you don't have to have a rock there. When the two surfaces touch, you got friction. And we have 100 newtons. Okay? Now, what is his motion? You're so smart. Who doesn't understand? Everybody's good? Okay. This is called, you know what this is called? Unbalanced forces. And now, mathematically, what is the net force? You writing all this? Okay, just checking. So, here's the rule. You must overcome friction for an object to accelerate or move, period. Does that make sense? Tell me what you're thinking. No? If I push on this book, I can push, but if I don't push harder than what's holding it there, it's not going anywhere. Does that make sense? Okay. It goes for slowing down too, but we're going to do that later. Now, our guy pushed off, right? And he's on his board, and he's just coasting. Right? You know what I'm talking about? Like, okay, but think about on your bike. This is I pedal, 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 pedal. And this is I just let my feet hang or roll my pedal backwards. And I just chill. Right? You get what I'm saying? Okay, so let's put the forces with that. He would still have 100 newtons that is making him go forward. Right here, he has 50 newtons of friction. And then he also has 50 newtons of friction right here. You know what this is? The air. Okay? What is his motion? He's not accelerating. He's not accelerating. He's just 50 newtons. 50 newtons. Make sense? So this is called balanced forces. And our net force is 0. Does that make sense? Okay. Now, let me give you the definition for balanced and unbalanced. We're almost done. Two forces equal in size and opposite in direction. Equal in size, opposite in direction. That's balanced. Okay? Your motion could be two things. At rest. Oops, forgot my T. Right? If they're balanced in opposite direction, I could be at rest or constant speed in a straight line. That is so important. The straight line thing. Yeah, because think about it. If I'm at constant speed, but I go to change lanes, what's going to actually make me change the lanes? A force. Like, think about driving. The cruise is on, but I need to switch over. That turn, that force makes that happen. That's acceleration. Okay? Unbalanced. Two forces not equal in size and this can be the same or opposite direction. The main key there is the amounts are not equal. On unbalanced, the amounts are not equal. And what's always going to happen? What's an unbalanced force always going to do? Yeah, cause you to move. And hey, guys, this could be speeding up or slowing down. You see this right here? If he doesn't put his foot back on the ground, what's going to happen to this number? It's going to go down. But guess what's going to happen to these? They can either stay the same or go up. It depends. But if this is not increasing, this is going down, then they are winning and he is going to slow down. You see what I'm saying? So that's why unbalanced causes your change in motion, and it can be to help me speed up or to slow down. Okay? One more word. Can you say this word? Equilibrium.
I think of it as math equal sign.
Yeah, it can be. You're right. A state of motion in which opposing forces are balanced. The net force will be zero. It's like balanced forces, but this is what they call the motion that you're in when you have balanced forces. You're at equilibrium. Does that make sense? So it's the same rules for balanced almost apply for him, but this is the motion you're going to get when they're balanced. Cool? Okay, awesome. Good. Y'all did good, and it was fast.